Hello, my name's Harry. Welcome to the screencast. In this video I'll be looking at making a measurement sweep with the 4191A impedance analyzer and then displaying that data in ZPlots. So in the previous video we calibrated the machine from 1 to 1000 megs. I'm now going to tell it where to save the data, put it in the download folder. I'm going to open the connection. I'm going to again reset the machine. And we're going to do a frequency run between 1 and 1000 megs, and I'm going to set the size of the frequency steps to 20 megs. That will result in 51 measurement points, which will coincide with the calibration frequency points, which will deliver the maximum accuracy from the machine. There'll be no interpolation done between measurement points, so that's just a little aside. Okay, so we've set the parameters. We'll send those to the machine, and now I've attached the device on the test, and we'll run the frequency sweep.
Measuring.
Okay, it starts at 1 meg and goes all the way to 1000 megs. I'll pause the video, and again we'll return towards the end. Okay, welcome back. So it's in the process of making its sweep, and in the meantime what we'll do is we'll open up another instance of Excel, and we'll point it to the ZPlots software. Okay, and again we need to enable the macro. Okay, so this is the ZPlots package. I'll include a link at the bottom, and many thanks to Dan McGuire for his excellent ZPlots. So that's the data saved. So if you recall, we said we put it in the download folder, so we'll go to downloads, last instance, and here we go. Here's the frequency sweep between 1 and 1000 megs. The red trace is the resistance in ohms, and the blue trace is the reactance in ohms. And if we go to the Smith chart, you'll see we've got a plot. Now I know this is a 75 ohm load, and it should result in a reactance or SWR 1.5. So we'll zoom into the 1.5 circle, and sure enough it's almost a very good match to that. Now there's one little flaw in what we've done, and if we go back to this control package, you'll see that we've set the electrical length to 0 centimeters. Now that actually is incorrect, because the device on the test has an N-type connector, and I needed to use an adapter to go from the APC7 to the N-type adapter, and that has effectively resulted in a phase shift which alters with frequency. So in fact these figures are incorrect. So what we'll do is we'll correct that, and I'll show you what the result should be. Now I happen to know that my test fixture has an electrical length of 3.16 centimeters, and we'll enter that into the machine, and we'll do another sweep.
Measuring.
And in the meantime I'll take snapshots of those two values. Okay, and we'll also take a snapshot of the Smith chart. Okay, so we're doing a second sweep now with the correct electrical length, and I'll show you how the two compare, and you'll understand the importance of entering the correct electrical length. So we'll pause here and we'll come back at the end. Okay, so welcome back. So it's just about to complete the second run.
Measurement saved.
So now we've done a second frequency run, but with the correct electrical length entered, and I'll now load that corrected data. And if I toggle the snapshot, you'll see the result. So you'll see, without entering the correct electrical length, effectively what happens is you rotate. You have a frequency dependent phase shift. So at 1 meg there's very little error, but as your frequency increases, the effective phase shift increases, and so the resultant error increases. So this is the correct result. This was the incorrect. The green is the incorrect result, and it gives you an indication of the importance of defining the correct electrical length. And again, you'll see at low frequencies there's little error, but as the frequency increases, the error becomes ever greater. So we'll turn off the snapshots, and you'll see this is the correct information. Okay, now within ZPlots you can put a marker, and you can move that marker along the 51 measurement points, and you can read the resistance and the reactance, and indeed the SWR. Now for a 75 ohm load, the SWR should be 1.5, and we can see we're quite close to that. Okay, so that's an example of how to make a measurement, but also the importance of using the correct electrical length. So anytime you add an extension to the reference plane, you have to measure that extension and enter that value in. Okay, so I hope you found that series of videos useful. You can see that the 4191A is still quite a useful machine, and in conjunction with ZPlots you can extract some really quite useful information from it. Okay, so thanks for watching, and hope to speak to you soon. Take care.